we were talking about the Vasicek model, right? So we were trying to understand the different nuances of the Vasicek model and how is it that it finally results in the this single risk factor model, right? In an attempt to do that, we started exploring the different components of the credit risk, right? So we started from the point where we had the asset equation path. From there, we had designed the asset path. Now, from there, we identified that the probability of default is driven by the Wiener process or the Wiener variable, or as we call it, the Brownian motion variable. So, if the the Wiener variable is less than certain value Ci, then then a default happens. Whereas if Wiener process value is greater than equal to Ci, then it's a point of no default. So the probability of a borrower of an ith obligor to default is nothing but the fact that the Vasicek, the fact that the probability or the Brownian motion is less than a particular value Ci. Now this Ci is or as a variable is something which is a kind of so like if I talk about the Ci contains or it explains some of the important factors which needs to be taken into account to express the default, right? So it talks about the liabilities. So the higher everything else remaining unchanged, higher the debt obligation, higher is the chances of the account to default. Higher the initial asset value or the asset path, lower is the chances of the borrower to default. Right. So these are so it identifies the key sources. Now from there, the next question that came out to us was that what exactly is this WAT, right? So what exactly is the Wiener variable over here? So in that case, what we are trying to do over here is we started splitting up this Wiener process variable. We said that there are these two components. One is economic specific risk or an industry specific risk. It's an industry specific risk, right? That's one. And the second that I said is the one is second is the company specific risk or the random risk. So the company specific risk is the risk which is which is specific to the company, right? So that is what is the company specific risk. So what we are saying over here is that the Wiener process is comprised of two parts. One is the industry specific risk, and the other is the company specific risk. Right. So one case what we see over there is that it contains this. So one is the y root rho and the other is zi root 1 minus rho. So when I talk about rho shows the correlation coefficient of the extent of correlation between y and zi. Right. So from there, what we also did was we started identifying that what would be the joint probability distribution of the loss. And from there, what we get to see is that the joint probability distribution turns out to be nck minus n plus infinity and the entire probability distribution, right? And from there, what we did was we converted this into this relationship in terms of the y root rho and c1, right? So it says that the relationship is that if the borrower is to be a defaulter, right? Then y root rho plus z1 minus 1 minus root rho plus c1 root t. This sum has to be negative, right? And it shows that. So if you look into the set of all these factors over here, if I take the list of all these three factors, right? So if you take a look into all these three factors over here, now what you get to see clearly, or like what you get to see very clearly at this part is that these three core components, right? These three sources are the core components of the risk. So your risk is either caused by your economic specific factor, or your risk is caused by any random factor which is arising from within your company or within the yes. So basically within the commercial organization. The third is the loan specific factors, loan specific or the obligor specific, or as we call it, the behavioral factors, right? So the economic specific risk is something to which all the obligors are exposed to. The company specific risk is something to which one specific obligor is exposed. And over here, CI root T shows the factors which the behavior factors, like the initial factor of the loan, the initial amount of the asset, the loan amount that has been taken, the growth rate, the fluctuation on the behavior. So CI shows the behavioral factors, right? So the overall risk assessment of a borrower is done in terms of these three characteristics, right? So this is where, so this is the core theorization on which the entire Basel model or the entire risk management models stand, right? And these models are offshoot of the insurance models, right? The actuarial models that are there. So if you think about this entire stuff over here, so if you think about this entire stuff over here, you'll see that in this equation, right? So within this entire equation, what we can capture are all the possible factors of credit risk. Now what we'll do is, now from here our objective is finally to reach uh our objective finally over here is to reach to the loss distribution, to finally understand what the loss distribution is like, and what are the core components of this loss, or what are the core components of this probability of default. So over here you can see that P is the probability of default, right? What we have said is PK is the probability of the kth loan to default. Now what are the factors which is affecting the probability of the borrower to default? That is what we need to study over here, right? So I'll not be going much into the kind of the very detailed mathematical calculations over here, because there are a lot of other factors which also comes in. So what I'll do over here is I'll try to kind of understand the overall behavior of the model, right? So we'll try to obtain the essentials of this particular model, the essential results that this model has to provide. So we look into that mainly. So before going into that, right? So let us just very quickly try to recapitulate a very basic concept, and that is the concept of a function. Just creating some So let us very easily let's very quickly try to understand the object, the basic concepts of a function. So as we have already discussed once, like y equal to fx is called a function, right? So what it says is that given a value of x, I'll get a corresponding value of y. So over here, x and y are in a causal relationship, right? Say for example, price of a commodity causes the demand of the commodity to fall, or an increase in the price of the commodity causes a reduction in the demand of the good. So over here, both x and y are in a causal relationship. So let's try to understand what is this causal relationship. So what it simply means is that x causes y. So x causes y. Now over here, then x is the independent variable and y is called the dependent variable, right? Now a very important concept in function is, or a very related important related concept is the inverse of a function. The inverse of a function, right? So what is the concept of the inverse of a function? The inverse of a function is not the reciprocal of a function, right? So this is often confused. So people often confuse this between the inverse and the reciprocal of a function. So basically say if y is a function of x, so if y equals to fx, so this will imply x is f inverse y, right? So what is that value of x, right? Or what is that value of y which solves for a given value of x? So over here, say I have a function like this, say y equals to e to the power of x, right? Now, what I want to understand is that if x was to be the dependent variable and y was to be the independent variable, then what type of a function would have generated similar values, right? So if y is e to the power of x, then what type of a function would have, so so if it was just the other way around, if y was to be made the independent variable and x was to be made the dependent variable, what would have been that functional form, right? So this is what is the idea of inverse. So when y is equal to fx, that is when y is the dependent variable and x is the independent variable, and corresponding to each value of x we get a unique value of y, then corresponding to that, right, what we want to understand is that given that, so given that y is a function, so basically then the inverse of a function would tell me that what would have been the value of x corresponding to a given value of y. So that is, if y would have been the independent variable, what would have been that function which would have given me the same values of x. So over here, what we do is, the way we generally do this is we take a log of both on both the sides, right? So from here what we get to see is that x is equal to the log of y. X is equal to the log of y. So the log function is an inverse of the exponential function. This log function is the inverse of the exponential function. So is the concept of inverse clear to us? The inverse of e to the power of x. Great. Karan, Vishal, is this idea of inverse clear to you? Because this is this inverse which will be coming out very, you know, would be something which we would be using day in day out, because when you go into capital calculation and all these inverse will be coming in. Okay, great. So over here, so similarly, say for example, I say that the probability of default of an ith borrower is nothing but the probability of the Brownian motion variable So this is obtained from the cumulative distribution function, the normal cumulative distribution function. So what we can also say is that the PDI, the probability of default for the ith borrower, is a function of the normal cumulative distribution from SCI is obtained. So what I can also say is that N inverse PD of the ith borrower is equal to CI. So N inverse PDI, N inverse PD of the ith borrower is is equal to CI, right? So this is a very simple relationship which we can clearly see existent between the variables, right? So if if I write PDI as small p, so PI is equal to NCI. So this clearly means that CI is nothing but N inverse PI. And this PI that we have over here, right, and this PI that we have over here is my through the cycle PD, right? So we'll come down to this through the cycle PD, then your point in time PD and so on. So So from here, so now what we'll do is we'll go back to the part from where we had started. Now, before we move on, let's look quickly into some results. Right. So we had talked about the Wiener process, and from there we had seen that uh, we had the following relationship. So one thing we saw that the Wiener process was defined as a part of two components. One was the economy specific risk, and the other was the company specific risk. Then minus. Now, over here you can see one thing that y root rho less than. That is y less than minus ci minus ci minus zi root 1 minus rho by rho root rho. Now, can you tell me why did I do this transformation? So, why was this part needed? So, we had seen that this was a relationship, right? So we said that the WAT, right? This WAT was comprised of these two parts, and this was less than minus CI. So, the question that comes out over here is that why is it that I am making this transformation over here? Any idea? What am I trying to do? Okay, standard normal distribution. No, this is not standard normal distribution because it's not of the form x minus mu by sigma. It's not of that form. What am I trying to do exactly? Yes, I'm trying to calculate the dependent variable value, but why this transformation? This transformation is there because I am pulling down everything to one single risk factor. So what I've done over here is I'm pulling down everything into a single risk factor. Down everything to a single risk. a single risk. Right, so so this is what the idea is. So I'll be pulling down everything to a single risk factor. Now, so this is one part of the block, right? So now the next part is to connect the two blocks, and from there we'll get an idea about the probability of default. Right, so now we are actually pulling in all these blocks that we have studied, and we are bringing them into one part. And on one side we had the Brownian motion variable, we have done that. From the other hand side we had the PD equation which we had obtained from the asset path, we had brought that. Now we need to connect these two to the portfolio equation which we had created, right? Now have a look into this. So what does this part tell us? What does this equation tell us? So this gives you an idea about the portfolio equation, right? Now over here, what we are trying to do is, we are trying to identify the fact that what are the chances that there would be k number of defaults in some n number of loans. And that is what we are trying to actually predict. And rather what we are trying to identify is the number of factors which affects that. That is what we are trying to do. So over here, observe that in this loan equation, there are a few important characteristics that we can observe. First is, there are only two possible outcomes. So there are just two possible outcomes. What are the two possible outcomes over here? In this expression that we are looking into this, this portfolio loss distribution, whatever. So what are the two possible outcomes? Yes, so what are the two possible outcomes over here? The two possible outcomes over here are either they will default or not default, right? Default, not default. That is, over here we either have a success or a failure. Right? Now, since I'm trying to model the probability of default, my event or my success factor is the default. Right? Now, let's think about this case. Now, for every success, right, there is a probability. Let's call this probability P. Right? And there is always a probability of failure, which is Q. And this is being repeated over n number of trials. N number of trials. Right, so it will be done between n number of trials. Now over here, the question that comes out is the following. So basically there are n number of loans, right, or n number of trials that are there. So what I imagine over here is that each of the accounts that I have over here, right, to whom a loan is being given, they are all independent accounts, right? So your account is independent of my account is independent of Anirudh's account, and so on, right? So the n number of trials are independent trials. So what I'm talking about over here is independent trials, right? So like independent trials, and not only independent trials, right? So it involves independent and finite trials. So I have n number of trials. I have independent trials and I have finite trials. So basically, I give out loan to some n number of people who are countable, who are finite, and each of the loans I give out to them are independent of each other. So this is what the independent and finite trials are all about. Correct? Now coming to the next part. So over here, what we need to understand is the following: that there is these two possible outcomes, success and failure, and in each of the trial, both can actually occur, right? And each of the trials are independent of each other. So if there are two independent trials, right, say A and B are two independent events, then the probability of A and B, the probability of both A and B to occur is nothing but, so if two trials A and B are independent, right, then the probability of A and probability of B are two independent observations. So therefore, the probability of success in trial A and the probability of success in trial B is probability A into probability B. That is P into P. So therefore, what I'm trying to understand over here is, let's take the case where the first k number of accounts they go into default. Now, if the first k number of accounts go into default, then what will happen? So let's take the following case, right? So the first k number of accounts go into default. So first k number of accounts. First k accounts enter into default. So the first k number of accounts default, right? So if the first k number of accounts default, then what happens? In the first trial, default happens. That is probability of success or P occurs. In the second trial, again the borrower defaults. I mean the second IT account also defaults. The third account also defaults. So for the first n number of, or for the first k number of accounts, they default, right? And the remaining n minus k number of accounts are non-defaulters, right? So for the first k number of accounts, success occurs, and for the rest, failure occurs. So what is the probability of getting k number of successes in n number of trials? It is nothing but the probability k into q to the power of n minus k. Just check. Is this logic clear? Just check whether this idea is clear. Great. Now, observe that what I have done is, okay, Karan and Bishal, you both are also clear with this idea? Great. Now, observe one thing, that over here, the p to the power of k and q to the power of n minus k, whatever I've done, I've taken an arbitrary pattern. But who has guaranteed the fact that p to the power of k, or p is like k number of account, like who has guaranteed that the first k number of borrowers should default and the remaining must not default? It can occur in any pattern. It can occur in any kind of combinations. So therefore, what we do is, it can, how many ways the combinations can happen? I can select k number of successes out of n in NCK ways. So this is the formula for NCK, right? And this probability or this distribution is not, this expression is known as the binomial distribution. So most of the lending process that we have with us is basis the binomial distribution. So it has at its base, or at its kind of background, the binomial distribution. So most of the lending processes are binomial in nature, right? So therefore, we want to find out this probability of the borrower to default. You can see that it is nothing but it's an exercise of, it's a binomial distribution exercise. So the probability that exactly k number of borrowers will default from n number of borrowers is a binomial distribution, right? And that is where this concept comes in. Now what I need to do is, I need to understand the probability of success and the probability of failure. Now what is the probability of success over here? The probability of success is the the probability to default, right? So if it defaults, then that's an event for us. Therefore, it will be nothing but the NCI, right? And the probability of failure will be what? Be 1 minus NCI. So from where did we get that NCI? We got that NCI from the asset price equation path, where we computed the probability to default is less nothing but the probability of the minor variable to be less than CI, and therefore that value of the different values of the CIs are obtained from the standard normal distribution. I mean the cumulative normal distribution. So the NCI is the probability to default, and 1 minus NCI is the probability of not to default. Right? Now, how do I write this CI? The CI has to be written in terms of the, uh, you know, this has to be written in terms of this y values, right? So we need to write it in terms of the y values. So how do I write it in terms of the y values? That is the conversion that I had done over there. I mean, in the next. If you go to this next slide, see that I had converted this, right? So now again, I can kind of reconvert this once again, right? So when I reconvert this, you see that right. So what one thing that I can do over here is I can reconvert this in terms of CI. What I can simply write over here is so. Uh, so over here, so one of our fundamental equation over here was y root rho plus zi root 1 minus rho less than also plus ci root t was less than 0. Right? So this is one of the equation that we had, right? Now from this equation, from this respect, we know that this relationship holds, right? So what I would like to do over here is very simple. I know that this is or this part shows my reflects my probability or the probability of the borrower to default. So now my probability to default is this n, right? So over here, what I would like to do is now the probability of default is like WAD to be less than CI. So from there, one thing that we can clearly do is so over here. Just a moment, I'm just getting a bit confused. So over here, we have this following, right? NCK integration from minus infinity to plus infinity, right? Now this will be NCI to the power of k into 1 minus NCI to the power of n minus k. DNC. So this is my probability over a probability to, or this is what my portfolio probability to default is. Right. Now the question that comes out over here is the following. So now I know that the CI is nothing but the n inverse probability to default. Right. So over here, what we need to do is we need to write this CI as a kind of, we need to write this CI as, or in function, or as a function of these PIs, or in function of these factors which comprise the CI. So CI is something which is the value, right? Now the Wiener process is less than minus CI. So the next thing that we need to do over here is we just need to identify that, like, how is it that we are going to work with this CI. So if we have a look into this expression, right, y root rho plus zi root zi power of 1 minus rho minus less ci. If I have a look into this particular relationship over here, right. Now over here, if you look into this, you will see that this is nothing but your systematic factor, right? Because the portfolio factor is a factor which is affecting everyone, all the borrowers who are involved in the portfolio. So if there are n number of firms who are taken a role, or who are taken a loan, then y is going to systematically impact all of them. Therefore, in this Wiener process that we had, y root rho is not a random factor. Right? So over here, what we need to understand is this thing, that, so therefore Zi will be separated at a particular part. So I'll put Zi at one end, right? And what I'll have is Ci minus y root. This shows that Zi is nothing but minus Ci minus y root rho. So which clearly shows that Now this ZI can write it in terms of and say that it is N inverse P minus Y root rho. Um, right. So the probability of default now is nothing but the probability of default of an ith obligor over here is nothing but the probability of Zi to be less than N inverse P minus Y root rho by 1 minus rho, which is nothing again, it is again nothing but N of, or it's obtained on normal cumulative distribution of N inverse P Y root rho by root 1 minus rho. So therefore one thing, now you can logically start deducing from here. You can clearly see that now the PD of the ith borrower that I am talking about is now being determined only by this systematic. It is being determined only by one source of risk, which is the portfolio specific factor. So before I move on, I'll just take Karan's question. Why did we separate the Y above? How is it used? So Y over here. So over here, I did it in terms of. So first I separated Y in terms of Ci and Zi, right? Then I changed it and put Y over here, and I represented the entire thing in terms of Zi. So you need not consider this part. So over here, I have pulled down everything in terms of Y. So what you can see is that there is only one single risk factor which is impacting the probability, and that is those factors which are significantly impacting the portfolio, the factors to which the portfolios are exposed to. So basically the idea is that any change that happens right at a portfolio level, that will impact all firms which are there, right? So it says that it is not the random factors within the organization which is impacting the probability to default. What is affecting is the macroeconomic factors. I mean the factors which impact the portfolio. Now all the firms, assuming that they have a similar kind of exposure to that economic specific factor, right? The impact that their portfolio goes through will cause the probability, or will cause the probability of default to change. Now think about it like this. I have a credit card portfolio, right? So there are banks, right, who are doing credit card lending. Now a downturn comes out to the economy. Now, irrespective of whatever the other problems are, or what other, uh, you know, company specific risks are, right? So those company specific risks would not be impacting the probability of default. So how will the probability of default be impacted for each of these banks? So it is that now the portfolio undergoes a deterioration. When the portfolio undergoes a deterioration, what happens is there is an impact on the borrower's behavior, right? Now, given that impact, the borrower's behavior falls down. Given that the borrower behavior goes down, his income goes down, his vulnerability to default increases. So what you see is it is not the company specific risk which is happening. So what is impacting the probability of default of a borrower at an account level and at a portfolio level is the economy specific risks, right? So when this risk goes up, right, the probability of default goes up. So what we can see is it is this risk which is impacting the random variable zi. It is that zi impacting the PDI. Therefore, it is this single risk factor which is impacting the uh, risk, and therefore, so if there is a common factor which is affecting the entire portfolio, right, now, so that means what, that all the banks have a, assuming that all the banks have a more or less a common relationship to a given macro, to a given economic specific factor or to a given state of the economy, any degradation in their portfolio behavior in their portfolio would cause the probability of default to go up. So basically, if I have hired, like if I have originated inferior borrowers, right? If I have hired inferior borrowers, right? Then given a state of the economy, I will always be having a higher risk than a bank who has hired or who has originated good borrowers. So it means what? That it is the economy specific risk, which is assuming that the economy of these specific risks impact the all the firms in a similar way, right? Any degradation or any increase in the riskiness is a result of the degraded portfolio of the bank. Once the bank's portfolio, a bank's portfolio is more risky because their portfolio is more degraded. So that is all this states. And all you can see is that the probability of default. Now, if I put all these, now if I put all these values over here, right, you will see that the entire portfolio level probability of default is also a function of one single factor. And that is why we call it a single risk factor model, right? And the entire idea over here is that it is not the company specific random factor that is impacting the probability of default. It is the single economy specific risk factor which is impacting the probability of default, and hence the loss of the loss distribution of firm. I mean of the banks. Clear up to this point? Right? And it is this framework which helps us evaluate the risk at an account level and then aggregate it at a portfolio level. And it is simply the existence of this single risk factor. Had it been due to the ZIs, right? Had the risk have been due to the ZIs, then we couldn't have done that, because in that case, say for example, if you are working for a bank like HSBC, you are developing one model for MENA, you are developing a model for the HANA region, you're developing for the APAC region, right? And then you are pulling everything. Now, if it is the company specific risk which was to impact, right, then you could not have done a through the company kind of an aggregation, right? So, so what are you doing? You are doing it at HANA, you are doing it at MENA, you are doing it at APAC region, and then you are pulling everything together, and you are computing the expected loss at the bank level. How can you do that? Because it is the common risk factor which is impacting all the units of the bank across the globe, right? It is not the branch specific or the company specific or the region specific risk which is impacting. The region specific risks are random risk which cancels out, and it is that common risk which is impacting the riskiness of the portfolio. Therefore, you can develop the model at a account level and then pull it up or aggregate it up at the portfolio level. And this is precisely what the single risk frontier model talks about. right? And this model that we have over here, this formula that we get over here, this PD that I have over here is my through the cycle. So this PD that I get over here, so this PD that I get to see over here is so this PD that I get to see over here is the so this PD that I get to see over here is the through the cycle PD. And this one that you get to see over here is your point in time. So this one, the normal distribution of this value is nothing but this PD, right? And say suppose if I do an n inverse of this PD, I will get this one, which is your point in time PD, because this is conditioned on the macroeconomic situations. So through the cycle PD is a PD estimate which remains unchanged throughout a business cycle. So it's a long-term estimate of a PD and is done by taking into account, and it is done by taking into account a whole business cycle. Now the TTC PD is kind of a long run estimate and is a more conservative estimate. Now for capital reservation model, point through the cycle PD estimates are ensured, right? So through the cycle PD estimates are created, or through the cycle PD estimates are used because you cannot always change capital according to changing situations of the macroeconomic situations, right? So if the economy shifts today from a downturn to an upturn, you cannot reduce capital, neither can you increase your capital if it shifts from a upturn to a downturn. Therefore, when you are computing a PD estimate for a capital reservation purpose, you have to do a long run estimation procedure, right? And that is where this is the through the cycle. So that is why we call it a through the cycle PD. And the PD inside this functional, this estimate of the probability of default, the value Ci that we talked about here, is a point in time estimate because it is conditioned on a given macroeconomic or a given economic situation. Right? Anirudh? Great. Okay. So, so this is how the PD. So this is how the single risk frontier model works, and this is how the PD estimate is done. Now, so this is up to the theory point, right? So from the next session, we'll start working with the PD model. We'll try to understand that what are the steps of developing a PD model. How will I develop a through the cycle PD model? What is the difference between a through the cycle and a point in time PD? How does it work, right? And hence we start our model development exercise on the SAS platform, right? So we'll start with this from the next class. Okay. So thank you guys. Thank you for your time. Yes, Vishal, the next class is on Saturday. However, I may have to travel on Saturday because of official purposes, but I don't suppose it's nothing confirmed, right? If it's so, then I'll let you know. But otherwise, we are having it at 9. Sure, chalo. Have a great day ahead tomorrow, and let's meet on Saturday. Bye bye.